Welcome to iLectureOnline, and here's our next example of how we compare work and kinetic and potential energy. And in this case, we're going to be working with the inclined plane. When you look at this, you say, wait a minute, if I looked at video number 6 in this series, it looks exactly the same. The only difference is, in this case, we also have friction. There's a coefficient of friction between the block and the inclined plane, which means that all the work that we exert on the, or perform on the object will convert into potential kinetic energy, but some of it will be lost by overcoming the friction. So what we can say is that the work done that we put into the system is equal to the potential energy given to the object, plus the kinetic energy given the object, plus any energy lost due to friction. And so we'll also have to calculate what that is equal to, and we'll see that in just a moment. All right. Now, first of all, we can start with the basic definition that work done is equal to force times distance. Let's see again that we move the object a distance of 20 meters, so x equals 20 meters. That's the displacement of the object, like that. And so maybe we use the letter D for displacement. And we can say that the work performed is equal to force dot displacement. Again, these are vector quantities, and we have to use a dot product. But since the direction of the force and the direction of the displacement, maybe I'll just do the single arrow right here, we know that they're both in the same direction. That means the angle between them is 0, and this becomes F times D times the cosine of the angle theta, which of course is 1. And so we have 1,000 newtons. Not 1,000, I think I have only 100 newtons. 1,000 newtons would be a little too much. 100 newtons of force multiplied times 20 meters, which means it's 2,000 newton meters or 2,000 joules of work done. And that work will then be subdivided into potential energy, kinetic energy, and energy lost. Now, if we draw a little triangle here, we can then see that this is the height gained by the object by moving at 20 meters along the incline. And let's find out what that height is equal to. We can say that the opposite side h is equal to the hypotenuse d times the sine of the angle theta, because h is opposite to the angle theta right here. And so we can say that h is equal to 20 meters times the sine of 30 degrees, which is 1/2. So therefore, height is equal to 10 meters. Now that we know the height, we can figure out the potential energy gained by this object. This object will gain potential energy equal to mgh, which is 5 kilograms, times 9.8 meters per second squared, times a height of 10 meters, which is a total of 490 joules. So out of the 2,000 joules of work done on the object, 490 of it is utilized to give it the additional potential energy by gaining a height of 10 meters. Now, how much energy is lost due to overcoming the friction? So in order to figure that out, we need to find out what the friction force is. So we can see here that this is the weight of the object, mg. And this, of course, would be the perpendicular component, mg cosine theta. This is the adjacent component, mg sine theta. And then we have the normal force pushing back right here. And the magnitude of the normal force is equal to mg cosine theta. So that's equal to, I forgot my little equal sign. So this is equal to mg cosine theta. And then the friction force, of course, is equal to the normal force times mu. So let's go over here. So the force friction, which by definition is the normal force times mu, which would be equal to mg cosine theta times mu. Let's figure out what that is equal to. All right, so in this case, that would be the mass of 5 kilograms, g of 9.8 meters per second squared. Cosine of theta would be cosine of 30 degrees, and the mu of 0.2. So let's find out what the strength of that friction force is. So we have 5 times 9.8 times the cosine of 30 times 0.2, and we get a force of 8.5 newtons. That's close enough. All right, so we have a force of 8.5 newtons. Now notice the friction force is going to be pointing in this direction. So let me note that. So here we have force friction, and it's in a negative direction. Now, if we're going to calculate the work done by overcoming the friction, we can say that, of course, work because of friction is equal to the force of friction times the displacement. And notice these are vector quantities. But in this case, the friction force is pointing in this direction, and the displacement is in that direction. That's 180 degrees apart, which means that this is equal to the magnitude of the friction force times the magnitude of the displacement times the cosine of 180 degrees, which of course is a -1. So this is equal to 8.5 newtons times a distance of 20 meters times the -1. So this is equal to 170 newtons, of course, a -170 newtons, which is the work done by the friction. This is the energy loss part that we're talking about here. So not all of the work was put into potential kinetic energy. Some of it, 170 newtons of, not newtons. Newtons is force. I need joules. 170 joules of it was lost to overcome friction. And so that means that when we take this equation right here, we have the work done, which is equal to the potential energy plus the kinetic energy plus the energy lost. And so the work done right here, which is 2,000 joules, is equal to the potential energy, which we calculated to be 490 joules, plus the kinetic energy, which we haven't calculated yet, plus the energy lost of 170 joules. Now I say, well, don't you have a minus here? Why do you make that a plus? Well, the minus simply means that's the work done by the friction, which needs to be subtracted from the work done on the system to balance out the equation. So therefore, we have to add it to the right side of the equation. That means I can now calculate my kinetic energy. So my kinetic energy is equal to the 2,000 joules minus the 490 joules minus 170 joules. So that 590, that's 660. That means 1,340 joules of kinetic energy will be given to the system. Now, at this point, let's say I want to know what my final velocity is of the object when it reaches a distance of 20 meters. Since I now know my kinetic energy, and this quick calculation, I think I did that correctly, I can say kinetic energy is equal to 1/2 mv squared. So multiplying both sides by 2 and divided by both sides by m, I get v squared is equal to 2 times the kinetic energy divided by the mass, which means the velocity is equal to the square root of that. Which means if I now plug in the kinetic energy and the mass into that equation, 2 times 1,340 joules divided by the mass of 5 kilograms, take the square root, I now have the velocity of that block at the end of that 20-meter journey. So 1,340 times 2 divided by 5, and then taking the square root of that, and it would be 23.15. Just call it a velocity of 23 meters per second. And there's a really nice example of how work done on an object will result in increase in potential energy, increase in kinetic energy, and potential also in some lost energy to overcome friction. That's how we do that.